Good morning, everyone. Good afternoon, good evening, wherever you are. Welcome very much for joining us for today's MEPTEC IMAPS Semiconductor Industry Speaker Series. I'm Ira Feldman. I'm the Executive Director of MEPTEC, and I'd like to welcome everybody to today's webinar. In future webinars we have on July 29th, Raul Perez from Digital Papaya, CustomSilicon.com. He will be talking about the custom silicon development process. And then on September 9th, we will have Brandon Pryor covering the packaging market. We're planning to take August off, but if we'll let everybody know if we will sneak in some additional presenters in August. But we do have these two queued up, so please plan on joining us on July 29th and September 9th. Webinars start at 11:30 a.m. Pacific. If you're interested in speaking at a future webinar, please let myself or Dave Town know. And additionally, in terms of future events, we're very excited to let everybody know that we have converted the Known Good Die workshop to a virtual event on September 16th through 18th. It will be online, so that'll allow even a larger audience to attend. We have an excellent keynote from David Greenlaw from NVIDIA scheduled, technical presentations from Cisco, Advantest, Synopsys, Mulbauer, Form Factors, and other. And we're also very excited that Jan Vardaman, today's speaker, will also be presenting at the Known Good Die workshop. We will update at kgdworkshop.org shortly with the full schedule. In terms of organizations, please take a moment to consider supporting MEPTEC. Our memberships and sponsorships allow us to produce events such as this at no cost and make them available to the packaging, test, and design communities. If you'd like more information, please contact Betty Cooper or B. Cooper at MEPTEC.org. So it is my great pleasure to introduce today's presentation. We have Jan Vardaman from TechSearch International. Her title of her presentation is Market Growth Drivers, Key Segments in Advanced Packaging. Jan is the president and founder of TechSearch International, which she started in 1987, that provides market research and technology trend analysis to clients globally. She is the co-author of How to Make IC Packaging, a regular columnist with the Printed Circuit Design and Fab Circuits Assembly magazines, and an author of numerous publications and presentations. She is a member of all the key industry associations, and she, prior to founding TechSearch International, she was on the corporate staff of the Microelectronics and Computer Technology Corporation, MCC, which was the first pre-competitive research consortium in the electronics industry. It is my great pleasure to introduce Jan. We will be doing this in a more traditional style presentation, so I will open up the Q&A tool. Please ask your questions as she goes, but we will address them at the end of her presentation. The slides and recording on YouTube will be available early next week. We will send out an email to all the attendees when those are available. So don't worry, you will get the slides and you will get to watch Jan do her presentation as many times as you care to watch. So with that, Jan, I will turn it over to you.
Thanks, Ira. I'm going to be talking to you a little bit about the market growth and the drivers in the advanced packaging area, and I really appreciate the opportunity to talk with everybody today. First of all, we are looking at the economic issues resulting from this pandemic that we're in. The International Monetary Fund is predicting a 4.9% decline in the global economy this year. And what we're seeing is that 90% of the countries are experiencing lower per capita income. Now, that might not affect me directly or you directly, but it's affecting a lot of people. And what will happen is a prolonged pandemic really worsens those economic conditions. So countries around the globe are really trying to do a lot of increased spending in order to dampen this negative impact. The U.S. is spending about $3 trillion or more. Germany and France have proposed about $545 billion in a recovery fund. China's spending around $205 billion on projects ranging from 5G, rail, and power grid. And one of the things that we have to look at is the consumer purchases about 70% of the, basically accounts for about 70% of the GDP, of the economic activity here. And so what this does is it impacts our smartphone consumer sales and things like that. Now, fortunately, or unfortunately, depending on how you look at it, we've had some out-of-cycle purchases of things like laptops, tablets, and game systems. And so these things have actually, because these have increased, we've increased some of the packaging and advanced packaging that goes along with that. If we go to the next slide, which is there. So I wanted to look a little bit at the smartphone sales, because that's one of the key things that drives our industry. The IDC is projecting that smartphone shipments will decline about 11.9% this year. On the Qualcomm earnings call a couple of months ago, they had predicted at least down 10%. But there are some predictions of returning to growth in Q1 of next year, which we hope to see. We have noted that both Huawei and Samsung have seen smartphone sales declines. The China-based smartphone shipments were down more than 26% in the Q1 year over year. But hopefully all these things are coming back and we'll have some better growth as we go through for next year. And of course, the reason we're looking at this is because this impacts a lot of our CSP shipments. And I'll explain why as we look at one of the teardowns that we've done. If you look at one of the recent teardowns that we did, the Apple iPhone 11 Pro Max, we found like 123 packages on the board. That's a lot of packages. 89 of those were wafer level packages, either on the board or inside another package. And there are more wafer level packages in an Apple iPhone than there are in any other smartphones that we've looked at. We've looked at Samsung, Huawei, and others. Also, you'll remember that the application processor is in TSMC's info with a memory package on top, so that forms the info pop. And what we found in Apple more than any other company is that many of those packages are underfilled. And there's more than 30 chip suppliers in that phone. Very, very interesting teardown that we, of course, make available. Now, the 5G is still really the key to our smartphone sales, our future moving forward. At their earnings call, Qualcomm had predicted that the 5G smartphone shipments will be between 175 to 225 million units this year. Now, I'll remind you that most of that is the sub-6 gigahertz. We still expect Apple to launch their 5G smartphone, but there may be some delays on that, but hopefully by the end of the year. And then at that time, we will truly see what a 5G phone looks like. Now, IDC projects that the 5G smartphones will account for about 28% of sales by 2023, so it's a fairly strong growth market. And of course, this will drive our CSP growth and our wafer level package growth. And if you look inside, when we did some of our teardowns, we were checking the 5G phone. We found that the package count increased in looking at RF baseband and wafer level packages. And we compared a Samsung S10 to the S10 5G. And it had 1.8 times more RF baseband packages with 48% greater total package area. So it's very interesting because as we've looked at some of the other 5G phones, we've seen that they also have standalone baseband packages. And traditionally what we had seen was that Apple had been one of the few companies that had a standalone baseband package, but now we're seeing those more. And as we tear down additional 5G smartphones. We also see more filters. We see more wafer level packages on the board and a larger board area, so larger package area. So that's good for substrate suppliers. More packages is good for the OSATs who build those. So basically, even if you have a decrease in the phone shipments, if you can have an increase in number of packages, there will be some benefit. One of the other things that we've noticed about these 5G phones, when you get to the millimeter wave designs, you're seeing a lot of changes in the package design and construction. For example, the 5G, what this means is new radios, new modems, new power amplifiers, and new front-end modules. We're seeing a lot of system in package designs with fully integrated antennas. This antenna design capability is very important. Thermal and electric modeling are super important in this area. The electron migration compatibility and EMI shielding is very important. Now, if you look at a sub-6 gigahertz phone, in that case, you could put the antenna on the printed circuit board where it's traditionally been. But when you get to the millimeter wave, we're going to have that antenna very close to the RFIC. So that means you're going to have a lot more antenna in package designs, and we see that very critical. You'll also see a lot more, the shielding example you can see here from Amkor with selective conformal shielding and some compartment shielding. So you're going to see a lot of changes in the way that these are done. And of course, our most famous package today is from Qualcomm, who's shipping quite a bit of their designs. Now let's also talk about the 5G infrastructure rollout. That's a really big expansion going on in China right now with projections of about 600,000 base stations to be installed this year. Now most of that, remember, is sub-6 gigahertz. The millimeter wave will follow in a couple of years. And what this has done is it's derived a lot of demand for our RF modules, our system in package. We know that by March of 2020, China had already built about 198,000 base stations. And while the rollout continues in the US, it's a more millimeter wave rollout. You've seen some advertisement probably. The rollout in Europe has been a little bit slower in some areas because of the spectrum auctions were delayed because of the COVID-19, but we will see those continue. So the rollout will continue this year, next year, so it'll be over this period of time. So that's going to drive a lot of our package growth in these SIPs, the complex SIPs, a lot we expect to see laminate with the antenna and package designs. So we expect to see this really continue to be a driver, and a lot of the OSATs have actually reported good shipment numbers based on satisfying this 5G infrastructure rollout. Now, another area we've looked into is the consumer sector with one of the watch products. Smart watches had a 12% growth in the Q1 year over year. And Apple has the top sales in this area. They have about 55% of the market share. And when we did our teardown of the Apple Watch Series 5, what we found was about 104 board level packages, many wafer level packages, lots and lots of system in package, and more than 25 chip suppliers. So we've seen a lot of interesting things in these packages. The other area that we've looked into as people are trying to continue their manufacturing operations, we've seen people try to use different techniques. For example, this wrist product from Radiant to help people maintain their 6 feet distance. The workers at the Ford factory building the ventilators were using a Samsung wrist device that vibrates if another person got in within 6 feet of each other. And this technology uses Bluetooth and an RFID application software developed by a company here in Austin. So I think this is a very important development that's really, probably we could see more of this in our manufacturing areas if people were adopting this technology. And this would be directly driven by the pandemic. We've also seen, and will continue to see, increased implementation of telemedicine. I think that a lot of the physicians across the U.S., which there are over 1 million, will continue to be using this to see their patients. This makes you feel a little bit more comfortable in contacting your medical professionals. There are more than 6,000 hospitals in the U.S., and we have a lot of people trying to continue to do this. And what this does is it drives demand for laptops and some technology to use that implementation of telemedicine. So that'll also drive some of these things like the Netgear Orbi system that uses the FPGAs, QFNs, and wafer level packages. So we have a lot of things that normally we would see telemedicine, but it's just the growth is driven to a greater level than we would have seen in a normal case. Some other areas, as I mentioned at the start of this, we talked about the growth in laptop and tablet sales that were driven by the work from home and educational demand. And as I said, it was really an out of cycle demand. But we're thinking that probably we could see increased demand for laptops and tablets as some of the schools remain closed this fall, or as people opt to have their children learn from home. And of course, the more children you have, the more devices you'll have to have. So we'll see that continue. We'll see continued increase of telemedicine. We're seeing an increase in demand for networking equipment, data center and cloud computer expansion. And one of the things that we've seen and talked about a lot, especially in Q1 and some increase in Q2, was the server volume increase, which has really been driving a lot of our flip chip BGA substrate capacity demand. It's also been driving some of our DRAM demand and our DIMM modules. And I think that that's why we've seen companies like Micron shift towards supporting some of the memory that goes into these applications. The other area we've seen is the AI accelerator demand increasing. TSMC had reported that they are at full capacity this quarter for the CoWoS production line, and that's using the silicon interposer, if you'll remember. And then we see a lot of futures of designs, a lot more activity with the fan out on substrates such as ASE's Focus, the Amkor Substrate Swift, and TSMC's Info MS, especially as people want to look at how to put high bandwidth with memory. Of course, we continue to see Intel's EMIB technology as well as an alternative to a silicon interposer. So there's a lot of activities. And just because we're in this pandemic situation does not mean that we have seen any kind of slowdown in our R&D. I would argue that the pace has actually, we've tried to increase the pace. So that I think we'll see some of these new high performance packages being introduced next year in 2021. Now, I talked a little bit about the fan out on substrate, and that technology is very interesting because it's an alternative to silicon interposer. Basically, you're using, in the case of ASE, the RDL is a 2 micron line in space, as well as TSMC and Amkor. And you can do up to 3 RDL layers plus a UBM is what's typical. ASE's had this in production since 2016 for this high silicon network switch. They've also qualified their chip last. That was a chip first process. They've also qualified their chip last. We're going to see increased introductions of TSMC's Info MS. We're already in production. I'll show you in just a second with the Info OS for a network switch application. And then Amkor is bringing out their Substrate Swift with a lot of interest in their technology, hopefully moving into production soon. And this is the example. I actually held this part in my hand. It was the a split die from MediaTek that was done by TSMC on the Info OS process. It's a homogeneous integration. In other words, they took the die, divided it up, and fabricated two die out of the one die design. And so they had to design it specially where they could do the split die. 3 RDLs, 2 micron line in space. There's C4 bumps on this, no TSVs. And they said that the cost is slightly less than using a silicon interposer. So that's one of the reasons that they had opted for this technology. And they also have published work that talks about it offering better electrical performance because the RDLs are used instead of silicon. The dielectric constant's better with the RDLs than the silicon. So it's an interesting technology, and I think we're going to see more people adopt this moving forward. Like I said, the first application is really driving it with a network switch. So let's talk a little bit about this growth in the data centers and the AI accelerators. So what's really driving this growth is large amounts of data, such as the commercialization of 5G services that we talked about, smart factory, industry 4.0, remote working and these online meetings like we're having right now. And I'm willing to say that I think we'll still be having these online meetings through the end of the year. So that's creating tremendous demand for a lot of this data. We've also got a lot more internet shopping malls, movie streaming services. We're going to continue to see that for the rest of the year. And recently we noted that the IBM CEO says that this pandemic is going to dramatically accelerate the adoption of AI and cloud computing. So actually IBM is kind of banking on that happening. So you got a lot of cloud service providers such as Amazon, Microsoft, Google, Facebook, Baidu, Alibaba, Tencent, ByteDance, and many others. And you can imagine when you put in these expansions of these data centers, the amount of hardware that you're dealing with. And this is just an example here of one of the Google data centers. So, and of course, the AI adoption would be driven along with that, the same level of growth. Now let's talk about what this all means in terms of IC package substrate expansion. What we have seen is a lot of the IC substrate suppliers expanding capability for the capacity for the buildup substrates. The Ajinomoto is the buildup materials used exclusively, and we've been talking to them a lot. They are adding capacity to meet demand. What has been said is that there's a lot of server growth and networking equipment that's really driving a lot of this demand for especially the high performance. We also see new GPU and CPU offerings. And remember that these buildup substrates are still being used for the silicon interposer to support that, for the fan-out on substrate, and any of these active silicon interposers that I'll talk about in a little bit. The other trend that we're seeing is not only an increase in demand, but we're seeing larger body sizes and higher layer counts requiring increased capacity. So the combined demand increase as well as the capacity increase is really driving the growth in the substrate area. Not even counting how many buildup layers. It's something like almost 7% growth rate in area over the next 5 years. And so we are really seeing a tremendous push to add capacity by companies like Unimicron, Ibiden, Shinko, Kensys, Nanya, these companies and others that will be increasing capacity to meet that demand. I mean, you know, this substrate business is a fairly large business. When we did our global semiconductor packaging materials outlook with Semi, we charted it to be about a little over $7.4 billion industry in 2019. And it's continuing to show growth. Now, as we move forward, we're entering a new phase, and this is where we're spending a lot of time in our R&D. What TSMC says is over the next 10 to 20 years that this chiplet is going to be a key enabler for our industry. We're very familiar with what AMD did in their chiplet designs on an organic substrate. They're in at least their third generation on this. And TSMC has, of course, introduced the SOIC using an active silicon interposer. I'm going to talk about the Foveros technology from Intel. And the reason that we're talking about all of this chiplet business is because the industry is looking for a more cost-effective solution given the economic challenges of scaling, of silicon scaling. So just like we put that, the network switch, we divided it in a chiplet and a homogeneous integration. People are coming up with, instead of just designing these really, really large die that have a yield hit, they're trying to break that design up and fabricate smaller portions of it and then have it all come together and work as if it were one chip. And it's really powerful. That means you have to have a lot of co-design from the IC and the package. So you have teams of people working much closer together than they would have in the past. There's also a desire to reuse IP, some new test flows that we want to use, looking at, we've had some good reports of improved electrical performance with these, reduced power consumption. Now that is a very important, whether you're talking about anything from a laptop to a server, reducing power consumption is a really big deal. And that's driving a lot of our packaging decisions now. Also, we want to see faster time to market. And this chiplet solution is going to enable that, as opposed to trying to just to design one very, very large SoC. So let's talk about these a little bit more. In production already is Intel's Foveros, which can be found in Samsung's Galaxy Book 5. Now, the interesting thing about this product is it has reports to have a longer battery life. It's very, very thin, and there's no fan. So these are all very attractive features in driving your sales of notebooks. And so this is one of the things that this technology enables. And what this technology is it's basically taking an active interposer where you put different functions like power management, maybe some I/O controllers functions, voltage regulators, DC-DC converters, and you put that in the active interposer. And then you actively stack your die on that interposer using, in the case of Intel right now, it is a microbump. In the future, we expect them to adopt some kind of hybrid bonding on that. But the reason that you want to do this is because it reduces voltage drop. It's going to be a lot more efficient in terms of power. There's more immediate power delivery to the CPU cores. We're going to eliminate passives on the substrate. And you have better system-wide communication across these multiple chiplets to enable a lot of our communication. So it's a really powerful technology. And I think you're going to see more adoption, greater adoption of this over the next several years. So I think it's a tremendous opportunity that we'll see people designing to. And while you're just starting at the very early stages this year, I expect next year to see a whole lot more products using this technology. So kind of in summary, I'd like to say that we're seeing, continued growth in advanced packaging driven by a lot of different applications, despite the fact that we're in this terrible pandemic, and that the OSATs actually can benefit from some of this growth. We also see that even though consumer smartphones are expected to see some negative impacts now, we do expect growth in smartphones in the future, in 2021 and beyond, driven by the 5G infrastructure rollout and adoption. This infrastructure growth is very important. We're actually going to see that help the situation in China as they roll that out. We're going to continue to see this growth in the data center and cloud computing, driving our growth in servers, driving AI accelerators. And this is important because it drives our growth in high performance packaging, drives growth in the laminate substrate, and drives growth from memory. So these are very important areas that we see moving forward. And I'd like to thank all of you for your attention today and everybody for trying to help us all get through this pandemic and get it over with. So thank you. And I think maybe there's time for a little bit of question and answer.
Yep. Thank you, Jan. We do have some questions queued up in the Q&A tool. I can read them to you, but let's start with, you've touched on the OSATs briefly, both in terms of the technology and the business, but what do you think the impact will be to their overall business model, or a little more details on the technology or the business side?
Good question. So one of the things, when we started out early on in the pandemic, we were really concerned with some of these forecasts for lower growth this year with smartphones and things like that. But what we've seen in terms of revenue growth is that because there's a lot of advanced packaging going on, the companies that are participating in advanced packaging are going to be able to see revenue growth. We've actually revised some of our forecasting to say that we're expecting could be 3% growth this year or more, depending on how the third and fourth quarter go. A little bit nervous about first quarter next year, depending on what happens the rest of this year. But so we're cautious, and people don't really want to make, it's very difficult for people to predict how their revenue growth is going to be, but I think we can safely say that the OSATs that are supporting the advanced packaging efforts will actually see growth in their revenue this year. And that's very positive. Now, legacy products, if you're, totally counting on legacy products and things in the automotive sectors and stuff like that only, I think that's a bit of a problem.
So it's very market specific. Okay.
Yes.
Got it. Cool. Okay, I'm going to launch the poll so that we can give Jan some feedback, but if people will take a moment to answer that. And do you want to open your Q&A window there, or I'll just
Why don't you
read
just
these?
read me the questions?
Okay. Okay. A simple one to start. Is there an estimated number of base stations that will be added for 5G in the US?
We've seen that rollout's already started with AT&T, but it's in the kind of hundreds of thousands probably. We're rolling out more in the U.S. of the millimeter wave, and with that we're going to roll out some of these small subcells, and so we've seen numbers above 200,000 of those small cells to be deployed, and that's because the millimeter wave is actually going to need a boost, if you will. And so we need a lot of that small cell deployment, and that's going to take place in the urban areas. So that's where we'll see that deployment. Your towers, in some cases you can use a tower, you can do some modifications on your towers, but you're going to have to deploy more of the small cell growth. And I think that's going to benefit over time. Now, it's a continuing rollout, so it takes time to deploy that, but it's certainly happening.
Okay, and related to that, what do you hear about material development efforts or plans for materials? They said they can stand, but I would assume specific to millimeter wave frequencies.
We're seeing a lot of people bring into production the low DKDF materials. The materials that the issue that people have is they don't always perform as the specs on the data sheet indicates. So there's been discussion about how do we test to make sure that these materials have the properties that we think they do. And but we definitely see the need for those materials for both the printed circuit boards and the substrates in the millimeter wave space. And since that's really what we're talking about deploying in the U.S., that's a big focus. In some cases, I think the existing set of materials would be okay for the sub-6 gigahertz, but you don't get the full advantages with 5G until you roll out the whole 5G infrastructure.
Okay. Let's just do, okay. Two related questions here. One is, about the OSAT advanced packaging technologies getting closer to semiconductor processes, and the foundries are entering into the packaging business. So it's a question, is that occurring? And then the related question from somebody else is, will OSATs be able to increase capital spending to keep up with the fab's investments in advanced technology?
Well, if you're going to stay in the advanced technology areas as an OSAT, you really have to continue that investment. So we're seeing the same kind of investment levels maintained over time by the top companies. You also have companies like TSMC participating in this area of growth. I don't have the figures handy for 2019, but in 2018. TSMC had about 2.5 billion or so that they had in revenue just from the back end portion. I don't mean from the fab, I mean the back end, like wafer bump and assembly and turnkey, things like that, so and test. So, I mean, these are areas that are obviously, what we're seeing is the advanced packaging is more complex, it's a more expensive package, there's more expensive tests related to it. So we're seeing the companies that service that sector of our industry are going to benefit from greater revenue growth. And, in order to stay in that and service that, they have to continue to make those investments.
Right, right. And I think somebody commented related to this that TSMC is building additional IC test packaging facility in Taiwan. So do you think there'll be, and I know you're focused on the technology, but on the business end, do you think there will be either consolidation where some of the OSATs will, say some of the foundries will buy OSATs, or do you think they'll increase their own investment? I mean, TSMC might.
You know, I don't know if well, it's hard to predict what some of the merger and acquisition targets could be, but I think in terms of what TSMC has done, they're basically in the presentations they gave that at ECTC that Douglas, you gave, they talked about the front end and the back end coming so close together that you're really having to do some of the assembly and some of these really high end like SOIC and things like that right after wafer fab. You're not even going to send it to back end of line. So I mean that means that there's a certain set of the market that really has to have that close a coupling with the foundry. Or so it's either got to be a very strong partnership, or it's going to have to be, you know, in that space. Now, there's some other things where, I mean, obviously TSMC works very closely with all of the OSATs on some of these technologies. They don't do everything. So it's going to be a combination. And but we do see heavily investment for them building their new plant, with a lot of that being packaging and assembly. And so, I mean, I think in general, our industry, you know, you have to have continued investment. And this is not a one-time thing. You can't just throw money at this once and have it function well. This is a continued investment required over time to maintain the technical capability in our advanced packaging area.
Right. You gotta keep up with the technology treadmill. And back to the technology side of things, we have a question about how the Intel Foveros packaging structure, how does it eliminate the need for passive components? I believe you mentioned that. Is there something intrinsic?
Basically, they can incorporate some of that in the active interposer. You can
so
incorporate
like
all kinds of things in the interposer.
So because like if you need a capacitor, you draw the structure on it.
Put that in there. I mean, you could do it. It just is I think they refer to it as a lot of design flexibility.
Okay. Okay. And actually, this is related. Somebody asked if there's some new advancements on the advanced embedded substrates.
Yes, we have seen some. We've seen some work in embedded substrate technology. We have seen both active and we've actually seen some interesting things for the automotive sector in embedded. We've seen for power devices in embedded. We are seeing continuous in that. So it's, you know, obviously in the short amount of time I had, I didn't cover everything, but that's an exciting area as well. We also saw some interesting presentations on embedded capacitor functions from Samsung at ECTC.
Got it. And with the actual structure, do you think, this question is, do you think the advanced RDL will replace the silicon interposers, or will it just grow with the overall market? Do you think there'll be a shift? Or?
There's some companies, like if you look at Xilinx, for example, they use a silicon interposer. Why? Because they have these slices that they fabricate that each have like 20,000 connections that have to communicate with each other, each slice communicating with each other next to it. So they're going to continue with the silicon interposer. There are many things that are going to continue with the silicon interposer, but there'll be a lot of other areas that don't need the density of a silicon interposer, that can use these other technologies. I mean, Intel is, you know, wedded to their EMIB process, where they basically take an organic interposer, put the silicon bridge in, and continue that. And we expect them to use that for a number of applications. Right now, it's mainly AI accelerators, but we expect with their FPGA structures, but we expect them to go more into the server area with that technology. And then we have other people looking at these RDL structures that are fan out on substrate. And I think that that you'll see new packages and new introductions coming down the road, with lots and lots of people doing design work in that area. So there's never any one technology that meets all needs. It really depends on what you're trying to do.
Okay. And then related, are you seeing any progress at the EDA vendors to support all these advanced packaging technologies?
Yes, I mean, I've seen there's been a couple of good webcasts recently from some of the EDA tool companies, and they seem to be making progress working with companies. And you know, this trying to understand the design capability and design your IC and your package together is so important that I think you're seeing more discussion in that.
Okay. Wow, I have to apologize. The questions are coming fast and furious. Everybody wants to know from your expertise, which is great, Jan. On the chiplets, this is a reference to a specific platform. Any comment on the chiplet platform from Ziegler?
Yeah, Ziegler has an interesting platform they have introduced. In their aspect, you basically take a wafer level package, you design the chip as a wafer level package, and you can use some of they have a big library of basically of things you can choose from. And you design that and then put that on a programmable substrate, if you will. And I think that in the right applications, that makes sense. Obviously, you know, that's the thing about where we are in our industry right now. You really have to have so much design expertise and coordination on your supply chain to really take advantages of these technologies. But that's another one. I know they have some designs that have gone into production, and I think it's an interesting technology.
Yeah. And related to chiplets, there was a question: is how are the chiplets being interconnected? I've seen, you know, the concept of smart substrates, but they're asking, is it through an interposer?
There's programmable substrates. If you look at the original AMD technology, those chiplets were designed so that there's a lot of for lack of a better word, let me call it software. But the connection capability that makes that chip act like, if you didn't know better, you would think it's a single chip because it acts like a single chip. But all you've done is just fabricated these parts so that you've, you know, been able to get higher yield out of the parts, and then you put them together and it gives you all these other advantages. So I think that, you know, it's more than just, it's not just hardware, it's not just software, it's a combination of everything in design.
Okay, right. And but you not just the substrates. I mean, they could do die-to-die metallization. I mean, in theory, you could do wire bonding, but I'm not.
I think you'd be a performance limitation with that.
Right. Okay. And are you hearing any discussion as to like the limitation of the number of chiplets in a package? I mean,
we've seen some people talk about, you know, you could do 9 or 10 or something like that. I don't know what the theoretical limit is. I guess it really depends on what you're designing and some of your, you know, your functions and things that you're doing. But I mean, I think that we can expect to see up to 9 or so in production in the not too distant future.
Got it. And closer to a topic that I've been involved in, you didn't touch on panel level packaging, and there's a number of people who have been interested in that.
You know, we've had, you know, obviously the Samsung watch uses a panel level package that basically is like an embedded die, where you put the application processor and the PIMIC very close together. And that watch has very long power, you know, longer battery life, low power. And so there's some other applications. We've seen some PIMICs, we've seen some other things out of companies. But I think I mean, the reason you go to a panel is really to get lower costs, but you have to have really high volume of a product to put it in that panel to make it make sense. And there's always been a question of how many panel lines do you actually need to support that? I think there's a little bit of confusion on the term panel, because basically when we make a substrate for a flip chip or anything else like this, the substrate is actually made in a panel. I think what people get confused with is a fan out panel where we have a lot of molding going on, and it's kind of like an embedded die, versus panels where we're fabricating a buildup layer on it versus where we're talking about transferring an RDL to it to make it super high density. And we're actually continuing to go and look at some of that research and what the issues are in fabricating really fine features for that in the next report that we're putting out, which will come out early next month. And I think that we've been struggling as to how to explain to people, you know, the difference in all these terms panel that are being used. And I think it's loosely being thrown around, and it's really confused people in the industry, and that's really unfortunate.
Right. Yeah, when we have confusion, it's hard to really understand what's going on.
Hard to move forward with confusion.
Yeah. Let's do one more question. Was related to when will hybrid bonding begin to enter production and then high volume manufacturing?
Well, I think that I just before this broadcast today, I was on two Zoom, no, a WebEx, a Zoom, and a Teams, three presentations ago today. I was listening to the Xperi presentation about the hybrid bonding, and of course we know that the Sony image sensors using that technology. Samsung uses that technology, and that's in the image sensor space, so it's already there. We know that it's been licensed to SK Hynix. We know that the flash memory company in China says that by the end of the year, they'll ship some product where they basically take one layer and do some wafer-to-wafer bonding. We hear people talking about the possibilities of doing HBM with that, although currently we're doing a microbump. The hybrid bonding is what TSMC is using in their SOIC technology, and that will be in their chiplets design, and that will be in production next year.
Great. There's far more questions here than we have time for, so I would suggest people reach out to Jan directly for the ones that you have the most burning desire to have answered. She probably has some good research information on a lot of it. Jan, any closing comments?
Well, thanks everybody for joining this. It's really an exciting time, you know, and several of us have talked about this, that this focusing on the advanced packaging and all these new developments in this very exciting industry is helping us get through the pandemic. And we can always help each other through some of these achievements in development of AI, in development of technologies to help us safe distance. And everybody just stay safe out there, and one day we'll all get together, and please wear your mask.
Thank you, Jan. Let me, and I thank everybody for attending. Let me just put some closing slides up here. So thank you for attending today's Semiconductor Industry Speakers Series presentation. Thank you again, Jan. It's always a delight talking with you. Reminders of the future upcoming webinars on July 29th. We'll have Arul Perez from Digital Papaya. And on September 9th, we have Brandon Pryor from Prismark Partners. We will send out email, but you can always check out the next webinar on MEPTEC.org. So I thank everybody. If you haven't had a chance to do the poll, please take a moment to do that. And we'll send out email when the slides and recordings are available. So I thank everybody and wish you a good rest of your day.